Okay, good evening. This is week 7. It's on a Thursday. Sorry, Tuesday, not Thursday. What am I thinking about? And today we're going to complete our example of unsymmetry shear example, and then we're going to look into combined loading analysis. Okay. So last Thursday, what we have done is we have discovered our shear center. Okay, we found our shear center. So we have found our E, right? And then we have applied load of 2.75 kilopounds of force. Now, the reason why we find this is to once we get the shear center, means we are going to prevent, or once we know our shear center, we are going to prevent the twisting due to unsymmetrical loading. And why this is under unsymmetrical loading, if I were to sketch, just to recall, if I were to sketch out a centroid, okay, for example, this is a sketch, this is our centroid. We realize that on the right hand side, it is less rigid, and on the left hand side, it is more rigid. When that's the case, the structure will tend to have a twisting deformation. Okay, you tend to twist. So when we have a shear center, all right, we know our shear center, we are generate a counter twist. Okay, and when we generate a counter twist, a twist and a counter twist is a couple, we prevent twisting from occurring. So only after that, then we can analyze the stresses. Okay, so now the next thing we're going to determine, we're going to find the stresses, or the shear stress distribution at, so we are asked to find at point A, at point B, D. Do we have a point C? No, D. I'm going to, later on, we're going to find the centroid anyway. Okay, the centroid, and then we have point E, F, and point G. Okay, so now we are going to construct our shear flow. Okay, we're going to sketch our shear flow. Now this diagram is available to you on Avenue to Learn. Okay, so like what we mentioned, the web control the flow. Okay. So what we realize that all these are our terminus. Okay, so all these are our terminus. 1, 2, 3, 4. Okay, so all those are our terminus. Okay, so usually note that the first moment of area at the terminus are equal to 0. Okay, so i.e. Q, not theta, sorry, Q is equal to 0. So from this, we know that the Q of A is equal to the first moment of area at D equal to the first moment of F and equal to the first moment of area of G, and they all are equal to 0. Okay, so therefore, the shear stress at point A, right, is equal to the shear stress at point B, is equal to the shear stress at point F, is equal to shear stress at point G, and they all are equal to 0. Okay. So before I go any further, we have to declare the shear center, right? E is equal to minus 0.927. Then from here, after we declare, then we can apply the formula that the shear stress is equal to VQ over IT. If we have not found the shear center, we cannot apply this formula. Okay, right. So we realize that shear stress at point A, sorry, not point B, point D, do apologize. Point D, point F, and point G are equal to 0. Okay, so we are going to look at point B. Okay, we are going to focus at point B. Okay, so I'm going to amplify the diagram for point B, make it bigger. Okay, so I want you to focus. So at point B, there are actually 3 critical points. No, or at point B, there are 3 critical sections. So you have one section over here. This is also point B. This is also classified point B. Okay, so this is also classified point B. So all these are in the point B region. Now you're pretty confused what we're trying to do down here. Okay, so we are going to call this this point over here point B flange. Okay, right? Why? Because it's more attached to the flange. The yellow portion that I'm going to highlight down here, this is the flange, right? So point B in the flange section. So this is the flange. Then we also have point B. I'm going to color in blue. Right, I hope you can see it. So this is point B. This will be point B. Okay, or point B wet. Okay, and then over here it covers both. Okay, so it's point B web plus flange. So point B, actually there are 3 sections or 3 subsection, as you can see. Okay, so the first thing we're going to find is the shear stress of point B, okay, at the flange, and this is also equal to point E at the flange. Okay, so same location now here, except this is point E and at the flange. Okay, so more important now is the first moment of area. Okay, so we're going to find Q. Okay, so draw our transformation Y Z. Okay, so QZ point B of the flange. Okay, so first moment of area from the z-axis, so it's equal to width multiplied by depth multiplied by y bar. Okay, so we know that the width is equal to 4 inches. We're taking the center line. Okay, again, I'm going to draw the yellow or the orange line where we are taking our dimension from. Okay, we are taking our dimension from this center line over here for everything. Okay, And I'm going to sketch our centroid. So this is our centroid. Okay. So the first moment of area about the z-axis, if it's on the z-axis, this will always be our width. This axis over here will be our depth. Okay. So the width will be 4 inch. The depth will be our thickness. So if you look at this question, the thickness is given to us as 1/8. Okay, times 1/8. Multiply by y bar, which is 6 divided by 2. Okay, so because the distance from here to here, this distance is 6/2. Okay. So our first moment of area will be equal to 4 times by 1/8 times by 6/2 is equal to 3/2 inch power. Okay. So from here, directly we can find shear stress at point B, just considering the flange. So the load is 2.75 times 10 to the power 3. Q is 3/2. I we found I is 2.7 no, not 2.75, 1/3, 233/12, and then multiply by the thickness is 1/8. Okay. So 2.75 power 3 times by 3/2 divided by 233/12 divided by 1/8 is equal to 1700 or 1700 psi, pounds per square inch. So that is the flange. That is very straightforward, right? And this is also equal to the shear stress at point E on the flange. Okay. So next we are going to look at the shear stress. Okay, we're going to look at the shear stress at point B and just considering the web. Okay, which is shear stress at point E, just considering the web. Okay. So the web section is the blue section that I've highlighted. Okay, so QZ at B for the web is equal to the width. So now the width is 1/8. Right? The depth is 2 inches. The y bar is 2 plus by 6 divided by 2. So 2 plus by 6 divided by 2 times by 1/8 times by 2. Okay. So it's equal to, wait, hold on. Probably I did something wrong down here. So this is not 2. This I have to 2 divided by 2. Because it's the individual centroid. I do apologize. Okay. So 2 divided by 2 plus by 6 divided by 2 times 2 times by 1/8 is equal to 1. Okay. 1 inch cube. Okay. So now again the same thing. Shear stress at point B. And for the web, so this is equal to 2.75 times 10 to the power 3 multiplied by Q divided by 233/12 divided by 1/8. Okay. So 2.75 power 3 times 1 divided by 233/12 divided by 1/8. This is equal to 1133 psi. Okay, 1133 psi. And then finally, we are going to find the shear stress at point B for the web plus flange.